So I will take you back to the sun, but also will propagate the solar wind to the very boundary of the heliosphere, where it interacts with a very local interstellar medium. Okay, the key challenges of our Blue Waters project are mostly based that we are modeling the flow of partially ionized plasma. So interstellar medium is very weakly ionized. Well, from engineering perspective, maybe not so weakly, but there are approximately 3 times more neutrals than ions in the interstellar medium. And for this reason, these neutral particles can penetrate very deep into the solar system and interact with ions there. So this figure illustrates the general pattern of the flow, really very simplified. The sun is at the origin, interstellar medium is from the left to the right, and they show the streamlines where they meet at the heliopause, which is a tangential discontinuity. Solar wind is supersonic, it decelerates through a termination shock, and under different circumstances, we can either have or do not have a bow shock in front of the heliopause. But neutral particles do not care about the heliopause, and they penetrate inside, experience charge exchange over there. So neutral particle, ion becomes neutral particle of the same properties, and vice versa. As a result here, for example, in the supersonic solar wind, we create neutral solar wind, essentially neutral hydrogen atoms propagating outward very deep in the interstellar medium and perturb the property, change the properties of the local interstellar medium in front of the heliopause. Neutral particles, which experience charge exchange over there in the solar wind region, they become ions. And these ions usually have properties very deep. First of all, they are never thermal. And this is very important, and for this reason should be modeled in principle kinetically. Its charge exchange also occurs every 50 or to 100 astronomical units, so it should also be modeled kinetically. So that's why we are solving coupled equations of magnetohydrodynamics equation describing the flow of charged particles, and kinetic Boltzmann equations for neutrals. If necessary, we also solve the Fokker-Planck equations for non-thermal pickup ions. And since there are non-thermal ions, they produce turbulence, so we implemented a few turbulence models which can heat up the background solar wind. So this slide actually shows the simulation, which shows the difference in simulations with and without pickup ions treated in separate population. We can add up pickup ions to thermal plasma. Of course, the temperature increases, and there are major effects of pickup ions are still seen there. But if we model them as a separate population, because in the difference is charge exchange between neutrals and ions, thermal ions and non-thermal ions, actually treating pickup ions as a separate population becomes of major importance, and this figure shows again the heliopause, the termination shock, and you see that in the simulation where pickup ions are treated as separate population, the termination shock goes further from the sun, while the heliopause approaches somewhat closer. As a result, the region between the heliopause and the termination shock, which is called the heliosheath, becomes thinner. Okay? So these results were obtained in the framework of this project by a former graduate fellow, Blue Waters graduate fellow, Matthew Bedford. So we also found out that the interstellar medium is perturbed to a very large distances of the order of 10 to the 5 astronomical units and more by the presence of the heliosphere. So this affects the propagation of cosmic rays towards Earth, where they are measured in different air shower observatories. Solar wind simulations from the solar surface to Earth orbit, they are also important for space weather predictions. And to address all these problems, we created a multi-scale fluid-kinetic simulation suite, MS-FLUKSS, which essentially solves all those equations I mentioned coupled, but on adaptive grids, and the grid generation and dynamic load balancing is ensured by the Chombo package. I will skip the structure because essentially I explained everything about this structure. Just very briefly, just showing that the strong scaling is nearly perfect, and weak scaling up to 120,000 cores is also just very good. So the new feature which is accessible now to MS-FLUKSS is to use the fourth order of accuracy in space is time, which is intrinsic to Chombo essentially, and using adaptive mapped grids like cubed spheres. Here you see, for example, patches of grids adapted to active regions on the solar surface. Why it matters? We do these simulations to interpret and spacecraft observation. And in some cases, we are even able to predict one observation or another. One of them is Voyager 1, which is very old spacecraft. But though it's 40-year-old, it's still there's no matching spacecraft, and there will be no other spacecraft of this type in a few coming decades for sure. So Voyager 2 is now in the beyond the heliopause and measuring the properties of the local interstellar medium in situ. So this is direct link to astrophysical observations. So it's very interesting. On the other hand, Voyager 2 is still inside the heliosheath, is measuring at the same distance, measuring properties of the solar wind, which are sometimes very different from what Voyager 1 was measuring, which gives us a hint that everything is very time-dependent and three-dimensional. On the other hand, when pickup ions experience charge exchange, and pickup ions, non-thermal ions, they have high energy tails. When they experience charge exchange, they create so-called energetic neutral atoms. These energetic neutral atoms can propagate backward and measured by the Interstellar Boundary Explorer. Okay, so these fluxes are, when they were first measured, it was determined that on a celestial sphere there is a narrow band of increased energetic neutral atom flux at especially at the level of 1 kilo-electron-volt. The explanation, our model actually already had it, we didn't know, but we had it already in 2009. In reality, this ribbon is a line of sight selection effect. So you see more ENAs which are created in the interstellar medium from pickup ions which gyrate about magnetic field lines. If we look in the direction which is perpendicular to the magnetic field line, and then the flux increases. The Parker solar probe was mentioned a few times already here. It's just a unique solar probe will swoop to within 4 million miles from the sun's surface. And one of the instruments where I'm a co-investigator on solar wind electrons, alphas and protons, will be directly exposed to energetic particles of the sun and measuring three-dimensional time-dependent distribution function of those particles, which is a huge challenge for future simulations. And by the way, it's Parker, it was renamed, it was initially Parker Solar Probe. Now the mission was renamed Parker Solar Probe, and Gene Parker is his contribution is just overwhelming in the field of the heliosphere. He essentially created this science, and this is, by the way, the first NASA mission that was named for a living individual. Okay, just right here, this was already shown in one of the presentations, I think it was Vadim, that each consecutive trajectory of Parker Solar Probe will take us closer and closer to the sun until it will be something like of the order of 10 solar radii. Just unbelievably close. It will be pretty hot over there. Now we talk about connecting the interstellar medium to the heliosphere. And it appears that observed anisotropy, and observed in many observatories, Tibet, Samarkand, Ice Cube, Arga, YGB, the anisotropy in the multi-TV cosmic ray flux is strongly dependent on the presence of the heliosphere, which was completely unrecognized by astrophysicists until it was the data was represented in this way as a sky map for particular energy. And if you look at the sky map, you immediately see that there are some strange boundaries between colors. And these boundaries are, in reality, we know them. Heliophysicists, they know them. These boundary right here, this is the nose, and which is essentially the direction of the local interstellar medium. And this magnetic field is where the magnetic field and perturbed magnetic field is directed. This is called the BV plane. We call it the BV plane. And this plane, this boundary is also a plane between blue and green. This is the plane where the line of sight is perpendicular to magnetic field lines, interstellar magnetic field lines, perturbed by the presence of the heliosphere. And this enhanced flux of a TV cosmic ray, this is the heliotail. It directly comes from the heliotail. So these all simulations we are performing on the using blue waters with plenty of support, mostly from NASA, but also from National Science Foundation as well. And I will just skip this slide, it's just only for the record. The past year, these are the accomplishments made in the past year only. We used coronagraph images from SOHO and Stereo spacecraft to simulate CMEs starting from the lower corona of the sun. We used also one Shili-Argy coronal model and driven by the Air Force data simulative photospheric flux transport model to simulate the solar wind properties at Earth and demonstrated advantages of our model over existing space weather prediction models. We also refined our model of shock propagation through the local interstellar medium. We performed time-dependent simulations of the heliosphere and showed that it produces a comet-like heliotail and that the ENA fluxes observed by IBEX from the heliotail are in agreement in our simulations. We also analyzed these TV cosmic ray flux by extending computational boxes to really very large distances from the sun. And it's very important because you can imagine that 5 TV cosmic rays, just roughly the duration radius is 500 astronomical units. So you need to modify interstellar medium maybe a little bit, but to very large distances. That's what we did. And we have used simulations to further understand MHD instabilities, the heliopause, and we reproduce the properties of pickup ions at New Horizons at in situ measurements published last year. The results were published, 6 papers, reported over 10 scientific meetings. Research was highlighted by the American Astronomical Society and also other web resources. Then briefly about if we do solar wind modeling, starting from the, if we are interested in space weather, commonly there are 2 approaches. One of them is physical. You start from the solar surface, you use observational data, and if you have enough observational data, you're hopeful that with a proper model, you will reproduce observations at Earth or maybe closer. So this approach is strongly based on using synchronic vector magnetograms. Magnetograms actually give us three components of the magnetic field. But from those, we can derive also tangential components of the velocity in the lower corona. And these 5 boundary conditions plus something else will allow us to perform simulations starting from the solar surface. This is just an example which shows a magnetogram here, typical magnetogram, longitudinal magnetic, radial magnetic field and longitudinal magnetic field. And right here, we reproduced the latitudinal and longitudinal components of the velocity on the solar surface. Excluding these blanked out are active regions. In active regions, we use a little bit different methods, but we also can extract velocity components. We don't see the backside of the sun, right? But we have EUV images from stereo, and such images allows us from, with certain accuracies, do estimates of what's going on the sun and create a full sun boundary conditions. Frequently, solar wind will not, these observational parameters will not give you the necessary strong coronal mass ejections. In this case, we created recently a data constrained model for coronal mass ejections. Or here you see this coronal mass ejection. This is the velocity, the solar wind velocity. These are magnetic field lines, and this is 1 minute after eruption, and this is 1 hour after. And this is done in the following way. We use multi-viewpoint observation images of coronal mass ejection, and then create twisted flux robes that evolve the way they do in observations. So this is radial velocity component, and this is magnetic field evolves right here. So I'll skip it. And this is the agreement comparison of the height versus time graphs of observations and simulation results, which also looks like pretty good. So these are simulations which I mentioned with boundary conditions with a less sophisticated, less physics-based model by Wang-Shili-Arji model. But it is very simple and allow us quick predictions of space weather at Earth. And here, right here, I show you different distributions of different quantities. Observations are red and blue are simulations. At Earth, we show that agreement can be very good. We have another solar wind interstellar medium interaction model with boundary conditions specified actually on the basis of observations at Earth. And right here, we show again, red is observations and blue simulations. You see that even very sophisticated simulations of Ulysses are just simply the curve is complicated. They're very nicely reproduced by simulations. With similarly at Voyager 2 and also in New Horizons. This is a radial velocity comparison with New Horizons, but New Horizons, right? New Horizons measuring not only thermal lines, but non-thermal lines as well, okay? And so we compare those density and temperature of thermal and non-thermal component, and the results are in very good agreement with observations. I mentioned that the heliopause is unstable to Rayleigh-Taylor and Kelvin-Helmholtz instability, but there's plenty of magnetic reconnection expected near the heliopause, which requires blue water simulations. We also identified as this very surprising thing in front the interstellar medium, when it's decelerated by the heliopause, its density is not increasing actually. It increases somewhat, but the distance of the order of 50 astronomical units, the density is actually going down. We call it the heliospheric boundary layer, and this existence of heliospheric boundary layer agrees with observations And this is, almost the last slide, it shows that how the this is how the heliosphere would look for extraterrestrial alien, probably. Yeah, we hope so. And these are observations. Let me skip to this file. These observations at Tibet Observatory for TV cosmic ray flux. This is, I showed already this figure. This is our simulations, which we performed just a few days ago, essentially last week. And the first time we were able actually to reproduce these boundaries here on the left and right hand side. And the heliotail is very good. So blue waters is because we need speed and we need a lot of memory. Broader impact, it's just we are developing codes that embrace coupling complexity. This is it. Okay, this is already very important. We greatly acknowledge support from all people from Blue Waters, especially Greg Bauer and Andrei Kot. And the help desk is essentially, everybody knows, is superb. And this is our future work, which is actually based on what we did already, and we will add turbulence and perform similar simulation in the presence of turbulence. Thank you very much for your attention.